Right. So, how we got into this area, sort of all stories lead into a direction, and you never know where you're going to go in research. Sometimes you've got ideas. And so we've been using carbon supports for maybe 20, 30 years. And a carbon support is just you put a catalyst on a support and to increase the surface area, basically. And we were funded by Sasol because they wanted people to work at Sasol. So we got money to get into this area. And then I was very lucky. We had a visitor, and I think many of you may know Professor C.N.R. Rao or know of his name. He visited WITS many years ago. And while he was here, I interacted with him, and he was making carbon nanotubes. He was one of the first people to really get into carbon nanotubes. And I sent a student over to his labs, and we started making carbon nanotubes. And that got us into the area of shaped carbons. And we've been using these, and we started using carbon dots about 7 years ago. So it's a winding story that gets us to where we are today. So the topic that really got me into this was Fischer-Tropsch catalysis, which in South Africa is one of the key areas of the chemical industry. And I'll show the big facility on the side. And it's a simple reaction where you just take carbon monoxide and hydrogen. It doesn't matter where the carbon monoxide comes from. It can come from biomass, it can come from coal, it can come from oil and gas and so on. And the key bit is that in the little bit in the green, the CH2, that's what you're making, hydrocarbons for fuels and chemicals. And that's the key reaction. And you use catalysts to do this. And the catalysts are typically iron, cobalt, or the industrial catalysts. So what's important, though, is that when you've got catalysts, you try and get a good interaction between the catalyst and a support material that spreads the catalyst. Because what you want to stop is agglomeration, which I show in the picture below. So you've got small particles of metal catalyst on a support. It doesn't have to be carbon. And what you're trying to stop is agglomeration because you lose surface area and then catalytic activity. So the supports are used, and you get what's called a metal support interaction, MSI. And in Fischer-Tropsch, you normally use metal oxides, but carbon has a weaker MSI, metal support interaction, and it allows you to study this process more easily. It's very easy to follow it by electron microscopy and other means. And so early work that was done in this area was on amorphous carbons, but in the 1990s, carbon nanotubes became available and other carbons. And so that's when we got involved in this sort of topic. So carbon itself is a fascinating element. It's a lightweight element. It's got variable bonding capability, sp2, sp3, sp, and so on. Abundant. Every country's got it. Associated with life processes. But for this talk, I want to talk about shapes, the shape that you can make these carbons into. And in actual fact, we've used all these shapes as supports in Fischer-Tropsch and other catalytic reactions. And you can see some coils in the top left-hand side, spheres, hollow carbon spheres, fibers, what are called horns, and sort of multiple shaped carbons in F. So many, many shapes. But the ones I want to talk about today are carbons with a spherical shape. And that includes fullerenes, which I show there, carbon black, hollow carbon spheres. But the ones I want to talk about are, in particular, carbon dots. And they're carbon dots and carbon onions, which are both at the same nanometer scale. And we wrote a review on this many, many years ago. You can see 2010. We weren't working in carbon dots at that time. We were working with carbon spheres and hollow carbon spheres and so on. So when we look at carbon dots and carbon onion-like materials or carbon onions, they have different shapes. And you can see the two shapes I've got in A and B. The one, if you look at, you've got to look carefully in the red circle, but you'll see graphene-like layers linking through, and you can see the size, about 5 nanometers. These are very small materials. In B, I show an onion-like material because it's a curved type structure. A pure onion would have a nice, complete circular shape, but these are sort of broken up into little bits and pieces that create the spherical shape. I'm not going to talk about the onion-like nanocarbons. You can also see they nanometric scale, 20 nanometers, typically even less. I'm going to concentrate on the carbon dots, graphene-like ones. But just to mention that when you make these onion-like nanocarbons, OLNCs, you need a high temperature. If you look on the extreme on the left, I show that you need a high temperature to make this, and you make it in flames, or at 700 degrees you need to make them. And they generally come out as aggregates, as you see in the extreme right-hand side. So these are the carbon onion-like materials. But I want to talk about carbon dots. And here you need much milder temperatures. You can make these typically less than 200 degrees centigrade. You typically use them, make them in an autoclave, but they're very easy to make. The yields are not great, and the separation is a problem because they're so small, but they can be made. And you can see my pictures showing lots of carbon dots. And if you look up closer, you start seeing the graphene-like layer. But it turns out in the area of carbon dots, there are a number of types of carbon dots, and I show the 4 types that are generally found. And the ones I'm going to talk about are the CQDs, the carbon quantum dots. These are the ones that have got a little more structure to them. The graphene-like are just simple 1 or 2 layers. The CQDs have many more layers, and the 3rd and 4th ones are more amorphous materials. They're very easy to make, as I mentioned. You can make them by top-down or bottom-up procedures. And if you top down, you just chop up big carbons and make them into little carbon dots. Or you can make them from small molecules. And this is the way most people make them today. You take small molecules, could be ethanol even. Matter of fact, in the old days when we used to do organometallic chemistry, you always used to get black gunk. And we always used to throw it away. And it turns out those were the carbon dots. We didn't know at the time. And so there's a lot of black gunk that is really just made of carbon dots. And they've now become sort of topical. We used to throw the stuff away in the old days. Oops, sorry. Yeah. So carbon dots. So when we look at carbon dots, they're pretty much thousands of papers that have come out in this area now. It's a very dominant area in the carbon area. And as I point out, the advantages, easy synthesis, any carbon supports, they're biocompatible, which is important. They're photoluminescent, I show a spectrum there. And they've got lots of surface functional groups to do things with. Problems is they aggregate easily, they've got a small size. They're used in many, many areas. I'm going to focus on catalysts and catalyst supports. But if you look at the literature, you'll see there's many areas in which they've actually been used. But for this talk, just talking about catalyst supports, not about the photoluminescence properties and so on. So when we look at the carbons themselves, they themselves can act as catalysts. And this is an area called carbocatalysis. And in this area, the carbon itself acts as a catalyst. I'm not going to talk about these. This would be another talk, in fact. I'm just talking about their uses. And I'll show acid-base catalysis, hydrogen bond catalysis, photoredox catalysis, and so on. So these can be used, these small materials can be used as carbocatalysts because it's carbon-based. But what I want to talk about is the catalyst and the support itself. And normally when you put a catalyst on a support, the support is the dominant part of the material. But because carbon dots are so small, and if you're using them as supports, you get what's called an inverse effect. That is, the catalyst and the carbon support that you're using is about the same size. And I show a picture there of cobalt with carbon dots on the cobalt. So we're looking at a different type of phenomenon here to what you normally see in supported catalysts. And this is called inverse catalysis. So I've got a picture there of cobalt with small carbon dots on top of the cobalt. And that's what we've been studying. we want to see what happens there. The carbon dots themselves, this is one example we've made. Pretty much you take ascorbic acid, which I show a picture of below, got a lot of functional groups. You heat them together, centrifuge, filter, and you've got your material. You know they're carbon dots because if you look at that little picture in blue, that's a scan of the layers, and you can see the layers are separated by typically what you'd expect for a carbon graphene-like material with multiple layers. The TEM images, just to give an example of stuff we've done, you can see they're about 5 nanometers in size. You do get residue, which is sort of interesting, and that's worth pursuing. We haven't pursued it yet. But on the extreme right-hand side is the stuff you filter off. And it's clearly, you can see that it's carbon dots that are sort of forming a sort of material that's sort of spread out and linked together. And I'll show you pictures coming up later, but not of the byproducts. Now, this is what happened unexpectedly when we started getting into this area. And this is really what my talk's all about, is that when you heat carbon dots just by themselves without any metal, what happens is in you may see little dots there. They're very small because the scale is 100 nanometers. But as you heat it up to 250, 400, 700, the dots themselves start forming films. And they form graphene-like films, graphene oxide-like films. So as you go from A to B to C to D, that's increasing temperature, and you see a conversion of the dots into a carbon layer. And these can be studied in themselves, and that's not going to talk about today as catalyst supports themselves. But you can monitor this reaction, this conversion reaction, which is an interesting one, by, for example, XRD. And here's an XRD temperature study where I've plotted the carbon peak, which is the one you're looking at, very broad, at about 20 degrees. And as you heat the material going from the carbon dot from A to D in the pictures, I'll show the temp pictures, you can see the peak shifts across. So clearly some change is occurring that you can detect. Now, it turns out there's a really interesting technique that many of you may be familiar with now, called pair distribution function analysis. And it's an XRD process in which you need a synchrotron, but you start looking at the XRD data where you are looking at amorphous materials. And what you get is a spectrum like I'm showing here, where you plot the distance angstrom against an intensity. And what you're looking at is a couple of peaks. And I'll show you what you're looking at is the distance. So if you look at that picture I've got of the graphene itself, where it's got numbers 1, 2, and 3, red, green, and blue, that corresponds to distances from that central atom. So when you go from central atom 1 to red, that's the distance. And in the plot, you can see I've got it down below, and there's a red 1, and that shows the distance about 1.4, 1.3, which is what you'd expect, 1.5, less than 1.5 for a carbon-carbon double bond. So, and I've listed the layers there, 1.4 to 2.46 and so on. So the pair size distribution function allows you to look at amorphous materials and get information about the bonding. And why that's important is if you look at the changes with temperature, you can monitor the change from an if you look at B going to A, which I show in the picture, that is sp3 going to sp2 carbon. And you can monitor these changes as you convert from a carbon dot to the carbon film or sheet that you make. So without going into detail, this is a technique for looking at amorphous materials. It may be useful for it is useful for other materials than carbon, but we use it specifically for carbon. And you can monitor the changes by this X-ray technique, but you do need a synchrotron to collect the data because you need a high intensity source. So what happens basically, this just summarizes the XRD and other material. We've got infrared data and so on that also confirms this. But you go from carbon dots, which I show, which is the purple with some functional groups on the edge, At lower temperature, you get a mixture of the two. And at higher temperature, you convert to sheets. So we see that coming through like that. So we now come to using these materials as a carbon support material. And in particular, our interest has been in cobalt as a Fischer-Tropsch catalyst, using these solid. So an example here, before getting onto the carbon dots, is to look at what we did with cobalt on a solid carbon sphere. So what I've got here now is carbon being the dominant one, with little cobalt species on top of the carbon particles. So we've got cobalt particles on top of carbon. So what's happening is we've got cobalt oxide under argon. Cobalt oxide, which is on the left-hand side, converts to cobalt on the right-hand side. That red with the sort of bluey color in it is converting to a pure red material. Cobalt oxide going to cobalt, purely under argon. So what's happening is the carbon is acting as a reducing agent. It's reducing the carbon oxide to cobalt oxide to cobalt. So I need to point this out before we move on to the next step, which is when we tried to use the inverse support and where the metal and the same size. But when we tried to do the Fischer-Tropsch catalysis on this, it was a disaster. We got pretty poor results. And the question is, what went wrong? So it has to do with that reducing ability, which I described above. What we were trying to get was this. You can see this is just an example taken from the literature of tungsten oxide covered with carbon dots. And I point out the carbon dot with that yellow arrow, but you can see many, many carbon dots on a support. And that's what we were trying to make. But clearly we make it. And the reason for this relates back to the carbon dots themselves. So what happens is the carbon dot itself, which is shown in the yellow, has functional groups around it. There's CH2OH, there's NH2, and so on. And what happens is, in the presence of a metal, these groups can act as reducing agents, and they can reduce the metal. They get oxidized themselves in the process. So the metal is reduced by the functional groups. The metal can be reduced by the carbon core, as I showed in the earlier slide, but the groups also act as capping agents to stop agglomeration. So we've got these combination of effects coming in when you've got carbon in contact with a metal. We can see the effect of this reduction process by these two slides. So let's start with the DTG, which is thermal analysis. What we're doing is we take our carbon and our metal and we heat them together and under oxygen as a function of temperature, and then we monitor the changes that are occurring, the mass loss. And if you look at the black line in the DTG, you'll see that there are two big peaks where the carbon surface groups are lost at about 300 and the carbon core is lost at 566. When we put the cobalt on, you notice that the peak at 300 has disappeared. In other words, all the functional groups have been used up in reacting with the cobalt metal. Also important is that the carbon core at 566 has moved to about 400 degrees in the process. So what's happening is the cobalt is actually catalyzing the loss of the carbon core. So there are two effects. The one is the cobalt reacts with the functional groups, and the second is that the cobalt then reacts with the carbon core to remove it. And so you can pick this up. The infrared just shows a similar effect where you can see one big peak, which I show with the red arrow, disappears when you go from cobalt dots to cobalt with, so carbon dots with cobalt on carbon. So when we look at the actual picture as an example, and this explains what's going on, is that you notice that in yellow, I've got a picture of a particle. That's a cobalt particle on top of what used to be carbon dots. So the cobalt has now aided in the carbon dots being converted into a carbon sheet, which happens without the cobalt, that also is catalyzed by the cobalt. And we can see the carbon just at 250 degrees has actually converted. We can monitor this by XRD as well. I've just shown a picture here with some nitrogen carbon dots, but it's not really important. And you can monitor this reaction going from cobalt, because what we want is cobalt metal as our catalyst. And we can see that only at about 400 degrees does this occur. So we can monitor this reaction and show that the conversion is happening under hydrogen. And more important is if we look at the carbon peak, let me just go back. So in the red block there, we can monitor not what's going on with the cobalt or what's going on with the carbon. And if we look at that in more detail, we can see that the peak is just moving across and quite different from when it occurs without cobalt. And eventually we get a junky material, as you can see on the side, which is a carbon layer with our cobalt, which is agglomerate. So the bottom line is that this is sort of an interesting study, but it didn't go the direction we expected, but it's opened up an area for making carbon sheets that can be catalyzed by metals. We can monitor this before what's called Fischer-Tropsch synthesis and after Fischer-Tropsch synthesis. And you can see, if you look at the bottom line, it's really just cobalt at 250, 400, and 700 in the bottom going from left to right. And you can see the cobalt is really there on a graphene sheet and the cobalt on sheet. So we can monitor these reactions, basically, showing that they really don't work. What we'd hoped for is a picture from the literature where they've taken rutile and covered it with carbon. This is what we had hoped to get, and where the carbon dots were giving nice graphene layers and the titania would be encapsulated. And unfortunately, that's not what we got. So to summarize and to conclude what's been happening here, if I look at the picture before looking at the conclusion itself, what we're doing is we're taking metal nanoparticles and carbon dots of about the same size. At low temperature, you can get this inverse support interaction occurring. I haven't spoken about that. I've spoken about the top one. Unfortunately, at higher temperatures, you get the formation of these sheets where the metal sits on the carbon, but the carbon now has formed sheets. What we'd like to have got was the bottom picture. And you can get that, but you can only get it at low temperature. So the picture's starting to emerge of what's going on with these type of systems. So if I can summarize then in the conclusion, we're finding the stability range for carbon dots, when you can use them in catalysis, when you can't. We found that the use of the pair distribution functions are useful. That's a new technique we've been using. And the next steps are to find that temperature range. Does a metal affect the type of carbon grown? We need to look at that. And how does this actually occur? Because I've said that we get these sheets being formed, but we don't understand how you convert from a carbon dot into a sheet at this stage. Right, the work was done by a group of people. I show the two, Roy Forbes, Rata Makaloko, two people I work with. The ones on the side are my collaborators. One's below, next to Lerato, or in the Fischer-Tropsch area. The others work in the carbon chemistry area. The work's been supported by a number of agencies, if you like, the two centers, the Royal Society of Chemistry, and I thank you for your attention, and I'll pass over to the chair. Thank you.
Thank you so much, Neil. I'll open the floor for one or two questions.